So this abstract stratification theorem and then let me write a blank here. And we had these support functions, and this is a bijection to Thomason subsets of T. And T is still an essentially small TT category. So in this abstract context with no more hypotheses, just Joachim Koch pointed me at the end of my lecture that what you classify is radical thick tensor ideals, and you can just guess what's the definition of radical prime. Yes, thank you. And radical, you can guess what's the definition. So you have A, tensor A with itself n times is in the ideal, then A is in the ideal. Yeah. Why I just wrote thick? Because I always have in mind that this essentially small TT category corresponds to the compact objects in a big category. And when the objects are compact and dualizable, then radical and thick coincide, right? So, so if objects are dualizable, and this is the case in which you are considering compact objects inside a big category, then you can just remove radical and just say thick. Yes? Then the thick tensor ideals are radical. Yeah, so that's a correction to Massima. I always had in mind, I always have in mind because that's the, so for the applications that we showed before, it was okay because they were all coming from compact objects in a big category. So the example back. So we had this example coming from finite spectra. Let me just fix a prime and localize at a prime. We had this thick subcategories Cn described by Morava-K theories, and we had this chain that has appeared also in its lectures. And here you can consider C infinity, which is kind of the intersection of all these Cn's. And that goes the other way around, sorry. Yeah, you should follow the convention. I tell my students that that's how you write it. So, and in that case, these are contractible spectra. And here you have all finite p-local spectra. And then you can just write this as a set as 0, 1, 2, and then n minus 1, n, yeah, infinity. And how the topology goes. So now the topology goes just in this direction. When you close, you go in this direction. Yeah, so the closure of 2 is from 2 to infinity. The closure of n is from n to infinity. So the topology goes in this direction, just to make clear the example, right? And then what the Hopkins-Smith theory tells you is that if you remove the p, then what you have a picture like this. You have rational cohomology here at the bottom, and then you start 1, 2, and then here you have the primes. In this direction you have primes, and here you have n, and then you have all this. You have this picture, and so on, and the closure of a point goes up. So this goes from, and you have infinity here in these tops. Yeah. So this is here. That's the way you can see the topology in this space, right? And so let me the support theory that is defined here. The support of an object satisfies certain properties. Yeah. So this is in the paper by Balmer. So it has these properties of the sup. And well, the first one is that the support of 0 is empty, and the support of the unit is everything. The second property is the support of A plus B is the union of the supports. The third one is that the support of the shift of A is just of the same as the support of A. And okay, this is front with up. And it has to do with exact sequence. Support of A is inside the support of B union the support of C when you have A, B, C suspension. Yeah, so that deals with how to relate the support. And then the last one, it has to do with a monoidal structure. The support of A tensor B is the intersections of the support. Yeah. So these are the properties, and that he shows that this topological space with this support is a terminal object in the notion of supports that you could construct out of this theory. So what I mean is that if you have for any pair X sigma, where X is a topological space and sigma is a function that goes from T into subsets of X, which satisfies A to E. This is kind of a support data for this triangulated category. Then there exists a continuous function that goes from F, that goes from X to the Balmer spectrum, and with the property that sigma of A is just it's the preimage of the support of A. Yeah, so it's kind of a terminal object in this set of data for which defines a support theory for T. Right? The pairs of X, subsets of X. I don't know if that's a standard notation. I mean, I think of X as a set, and these are the subsets of X. To each element of T, I associate a subset of X. That's, how it works, okay? So 5. So what's next? So, then it has to land in closed subset of X, yes. So now this is for essentially small categories. Many cases they come as compact objects in a tensor-triangulated category, right? And in these tensor-triangulated categories, you can consider localizing tensor ideals. So now the question is, can we classify localizing tensor ideals in a tensor-triangulated category using the Balmer spectrum? It's like you can classify the the thick tensor ideals, the compact objects, and you want to promote this classification to the localization, right? So so next thing is attempt to classify localizing tensor ideals in T, which is now a TT category. And then, well, first you might wonder whether this has been successful in history, and then we already know examples. Yeah, so examples come from the work of well, Hopkins and Niemann. When R is a noetherian commutative ring, and then they classify the localizing tensor ideals and the thick tensor ideals using, and now the spectrum they use is just the spectrum of a ring, right? Yeah, I don't need to write homogeneous here now. It's just an honest and simple ring. Yeah. And other examples is the Benson, Iyengar, Krause, where they just did the same thing using in the stable module category, the big one, not the small one, and using the cohomology of the group G. Here, K is, I just take KFP just to avoid technicalities, and then and P divides the order of the G. And let me tell you about an example, which is what I mentioned the last day, and I missed a lot of hypotheses. So I just jumped through my notes because I was running out of time, and the hypotheses were not in the statement, but before, so that will be also correction. And by doing this, by describing a bit how it works, the strategy we use is the same strategy that it was used in the case for Benson, Iyengar, Krause. So which is a descent technique. So I want just to say a few words about it. So the idea you have R, a commutative ring spectrum, and then you consider the category of module spectra of this ring spectrum that I will call mod R. You can consider it as an infinity category, all the good structure is in there. And you want to classify the localizing tensor ideals here. Yeah? So what we did is we used the Benson, Iyengar, Krause strategy of support. Yeah? And the first hypothesis you need is that the homotopy groups are noetherian. Yeah? And then what we did is to develop a descent technique. And just let me give you some key words about this descent technique. What you need is, okay, this is in the other. I don't want to miss more hypotheses this time. So I have a ring homomorphism. R to S and RS are both commutative ring spectrum, and with noetherian, when you take the homotopy groups, these are just graded rings, and then you want them to be noetherian. And so assume that mod S is stratified. That means that when I say stratify, in this I mean that you have this bijection between localizing tensor ideals and subsets of the spectrum, homogeneous spectrum of the homotopy of the ring. So in this case is the support functions will go to, from mod R, they will land in subsets of the homogeneous prime ideal of the homotopy of R. Yeah. So I'm not using the Balmer spectrum yet. Yeah. Yeah. No, I keep it. Yeah, but it will give you some nilpotent. At the end, it will not. It will not. I mean, it gives you some nilpotent part of this, which then you don't see in the spectrum. Oh no, then yeah, you just, yeah, there is no restriction. Yeah, you are right. Yes, yeah. So and okay, we have this map. We assume that it's stratified, and we have to, given this group homomorphism. Sorry. Yeah, we're assuming that mod S is stratified. Yeah, and the supports in both cases they land in the homogeneous spectrums of the homotopy of the corresponding ring. Yeah. So you've got S and then S, and then so we have two comparison maps between mod R. Well, we have three in fact. So you can restrict, you can induce, and you can co-induce. You have three ways to move between this module categories. So you have restriction, you have induction, because S is an R. You can think of S as an R module using this map, and then you restrict, and then you have a co-induction, which are the left and right adjoints to the restriction. Yeah. Okay, so you assume that this is stratified, and you also assume that induction and co-induction are conservative. That means that if the image of an object is 0, then the object was also already 0. So you can detect the 0 element using these two functors. Right? So you assume that these two are conservative functors. Conservative functors. And then, so what we show is that this is stratified, these two are conservative, then mod R is stratified if only if, and then, and we're also assuming, sorry, that F is a finite morphism. That means S is a compact R module. Yeah, so, and that S is in, as a R module is compact, right? It's a finite morphism. In this case, being stratified is if only if some Coulomb condition, you only are reduced to check one condition, what we call Coulomb condition. I try to explain now. But instead of describing these very technical conditions, I will tell you situations in which it holds. It has to do with the behavior of this map in the spectrum. Yeah? So for example, this is implied if when you look at the map from P star, sorry, S, at the map induced, you have these homomorphisms. It induces a map between the homotopy from P star of R to P star of S. This is a ring homomorphism. And then you have a map between the spectrum of homogeneous prime ideals that goes the other way around by taking pre-images of prime ideals. Right? So this is implied if this is injective. Sorry? Pi star of R, yes. Yeah. Yeah. So this is a very technical condition, but it can be checked from some properties of the map induced at the level of a spectra. Yeah, it has to do with something happening in here, in fact. Yeah. And this happens if, for example, the map between induce, the map from P star of R to P star of S has nilpotent cokernel. So if the cokernel is nilpotent, then the map induced in a spectre is injective, and this is one of the situations in which this condition is satisfied. Okay. So and then let's apply this one R cochange of BG. And that's the strategy somehow that also Benson, Iyengar, Krause just follow, is just in that case, what is going to be S? Have to give a good candidate for S, and this, it's going to be the product of cochange of BE, where E is a subgroup of G, which is elementary abelian. It's an elementary abelian P subgroup. It's just the product of copies of ZP to the R. So we are going to apply, we're going to descend this stratification property to elementary abelians. And for elementary abelians is something that is checked by hand. There is a ground case that you have to get your hands dirty. There is no way. And then you apply the descent technique with respect to this map. So the map from R to S is just, if E is a subgroup of G, then go from the cohomology of G to the cohomology of E, or cochange of G to cochange of E. Yeah? And then this is the map that we use to descend. And there are two important properties. One is you have to check conservativity of induction and co-induction. And this follows from some Chouinard's type theorem in representation theory. But I want to focus a bit on the Quillen condition, yeah? Because that relates to classical work of Quillen. So Quillen also appeared in the other series of lectures, so that's something classical. So this relies in the following work of Quillen, which, well, you know that the cohomology of G is noetherian. If it's noetherian, you can ask about invariance in commutative algebra that can be computed in a commutative noetherian FP algebra in this case, or in a commutative noetherian ring. So you land in the land of commutative algebra, and then you have invariance you can compute. The question is, can you compute this invariance without computing explicitly this cohomology? Is there any information about G which allows you to compute certain invariance? So one is the Krull dimension, yeah, and that's what Quillen did, but following this strategy. So he looked at the map that goes to the restriction to all elementary abelians. That's an elementary abelian P subgroup. Yeah, I mean it's the same indexing as there. And then this lands in the inverse limit. I mean, what you hit are compatible tuples in this cohomology. And compatible, what I mean is that it's compatible respect to inclusions and conjugations, right? So this is an inverse limit taking with respect inclusions of subgroups and conjugations. And that's the image of this restriction map to all elementary abelians, okay? And then he studied this morphism, and then what he showed is that this rho is an F isomorphism. That means that this map has kernel, the kernel and the cokernel is nilpotent. So you take any element in the cohomology of G that goes to 0. There is some power, some power of P of x to the P to the R, that it's already 0. And the other way around, you take any element in here, and you know that up to some power, it's in the image. It's hit by this map. So it has the kernel and cokernel are nilpotent. And that means that when you look at the spectrum, you get an homeomorphism of a species. So this induces an homeomorphism of a species, and this is a finite category you can commute, and the limb becomes a colimb, right? So what he shows is that you have an homeomorphism. Sorry, that's spect to the cohomology of G. So this is some classical and very nice work of Quillen that I really like. It's one of my heroes. And so that gives you a complete description of this topological space in terms of the spectrum of subgroups and how they glue together, doing inclusions and conjugacy relations. Yeah, so this category here is the same. Yeah. But he goes one step further, and then I think that's the reason that we use the terminology stratification in all this business. I'm not sure, but so this is called the Stratification Theorem of Quillen, and then there is the strong Stratification Theorem. I mean, this is some classical mathematics. That's the theorem of Quillen, which says that I can describe this topological space with a strata, with disjoint strata, and I can give you precise description of each strata in terms of elementary abelian. So, so he says that this is a disjoint union of, let me, I write some notation here. Yeah, so what's this? So this is the spectrum of the cohomology of E, where we remove anything which come from smaller subgroups. So E has smaller subgroups, which are also subgroups of G, and you look at the image of everything which is hit by a smaller subgroup, and you remove it. So the image of smaller subgroups, and then there is an action of the Bile group of E in G. That means the normalizer of E in G, modulo the centralizer, because the centralizer does nothing. And then you look at the action, and then you quotient by the orbit. So that, in fact, he says more. He says that there is a transitive action of this group in this image, and then you do the quotient. Yeah. Yeah. So it's a very precise description, and this is what he calls a stratification theorem, because it's a precise thing of describing a topological space in a strata. Yeah. So that's okay. So that's the classical situation, and that plays a key role on checking this Quillen condition. That's the reason we call it Quillen condition, because it's telling you that if you take any prime ideal of the cohomology of G, comes from an elementary abelian subgroup, and you can go and you can look for the smallest one that hits your prime. But you could have a different one. You could hit this by another. You could take another path. And what he's telling you is that any two different possibilities, they are conjugated. So if you have two minimal information from elementary abelians which hits your prime, there is a conjugation in G which takes one to the other. So it's really a strong statement. And that's what essentially is hidden in here. Yeah? And then we apply this descent technique to show that mod cochange BG FP is stratified, and G it's finite, but can be also compactly grouped now. And other, and in a general, and there are more general spaces in which we know the stratification of cochains of spaces. Yeah, so that's. But I didn't want to spend more time on this. But just to show you a technique, which is the same used by Benson, Iyengar, and Krause, they do this. They develop some descent technique, and then at some point they check BZP essentially by hand. Yeah, so that's okay. So. No, elementary abelian, yeah. Yeah, because the F isomorphism theorem works for compactly groups. I mean, the paper by Cullen is more general than finite groups. In fact, he does it for the cohomology, for the Borel cohomology of G acting on a space. It's much more general than this situation. Yeah. Okay, let's see. So there are some examples in which you know that you can deal with the big category. And you would like to develop these techniques in the context of tensor-triangulated categories. So there are two goals: to define, I should change, yeah, to define a support theory. We haven't done this yet. We only have a support theory for small, essentially small tensor-triangulated categories. We need a support theory for a big tensor-triangulated category, and then what does it mean to be stratified in this context? And then do we have descent techniques so you can compute new examples from other examples? That's kind of the 3 steps. So yeah, for example, yeah, let me just add something. Everything seems to be about cochains in this example. There is another example we could do, which is just you take the spectrum of KO and KU. This is complexification. This is complex K theory. And then you know that work of, I think it's Balmer and Dell'Ambroglio, and okay, I'm not sure I get it right. But they show that if the homotopy groups are concentrated in even degrees, then mod R is stratified. This is an example, one of those examples that you can do from 0 without a descent technique. And then we apply the descent technique to show that also mod KO is stratified, just from the fact that mod KU is stratified and checking the conditions on the descent. Not everything is about cochains and G, so you can work out other examples. Yeah, yeah. Yes. Yeah. So when this is surjective, this is related to the conservativity of the functors. In fact. It's nice because the injectivity of this map is related, not equivalent, but it's related to this Cullen condition, and the surjectivity and the Mile assumptions is related to the conservativity of these functors. Yeah. So I cannot say more without going more technical, but we can talk about this. Yeah. So yeah. Sorry. No, it's not injective. No, but it satisfies this condition. Yeah, yeah. So and the key point is that the key point is given by if you choose to. The point is that you have 2 choices of minimal elementary booleans and primes which detect your prime, they are conjugate. That's the key point. I mean, yeah, it's using this. Yeah, but just to, I don't want to write it, all of it, just to tell you that there are situations in which you can check it. Yeah, but that's not that case. Yeah, yeah. Okay. Yeah. So support for T, which T is a tensor-triangulated category, and this is done in work of Balmer and Favi. And I will sketch a bit what's going on. So we need some hypotheses on the Balmer spectrum of the category of compact objects in T. And I will require that this is a noetherian topological space. And I think it's enough, in fact, that it's weakly noetherian. And weakly noetherian will mean that if you take a point, which is a prime ideal, you can always write a point as an intersection of a Thomason subset with a complement of a Thomason subset, that you can kind of make these points visible using Thomason subsets. I won't say more about it, but this is, you can just assume noetherian. Yeah? So in that case, there exists idempotence. Let's G of P for each prime. These are objects in the category. These are in T. They are not going to be compact. Now they are in T. There exists some idempotence, and then you define the support of an object as those primes for which this is non-zero. Yeah, this is the way they define support for any object of the category. So these idempotents, they are not going to be compact. They are in the arch category, right? And this support agrees when T is compact, agrees with the previous support. So big support is a small support when the object is compact. So we are just extending the notion of support to all objects. Yeah? And then you can define the category. You can define the following category, which is that for each of these objects, you look at the smallest localizing tensor ideal category which contains this object. Yeah, and the idea is that these are kind of over each prime is like you are looking at kind of a stalk with these categories. Yeah. So all this stratification business somehow is telling you a way to reorganize your category in a kind of a way in which you have the Balmer spectrum, yeah, and then you have these stalks, and that's a way, it's kind of a bundle. It's not formally, I think it's not a bundle, but in my brain, in my imagination, it looks like a bundle. You have the spectrum, and then you have all these stalks on each prime. And that's a way to reorganize the information in your tensor-triangulated category. Yeah? And we define these categories, and then in a work of Barthel, Hart, and Sanders, and they develop the theory of stratification by using this big support. Yeah, and then they just describe these two principles that I just sketched last day, the local to global principle, which essentially says that if you look at the smallest localizing tensor triangulated generated by T is the same as the category generated by these idempotents hitting your object for each prime. Well, you can write the support of T. Right? It's like you can split, you can, this T gives you some pieces, and then that you can reconstruct T from the pieces. That's what this local to global principle. You can recover the global object from the local pieces that you obtain by hitting it with these idempotents. And the other is the minimality, which is that this log G of P are minimal localizing tensor ideals. And what they show is that this is equivalent to stratification, which means that you go from localizing tensor ideals, and with support you hit subsets of the Balmer spectrum of the compact objects, and this is a bijection. Just following what Benson, Iyengar, Krause did for just tensor-triangulated categories. No, for triangulated categories, sorry. Yeah? In this context, using this Balmer-Favi support. And then that means that to have this bijection, you have to check these two conditions. And the first condition is implied, they show that it's implied by the noetherianness of the spectrum. And then you have to check the second condition. Yeah? I want to make a remark here. To classify localizing tensor ideals, you don't need to know the topology. It's just subsets. Yeah, that's a point. You don't need to know the topology of this space, it's just subsets. But if you want to know the thick tensor ideals, you need to know the topology because you are taking Thomason subsets, which are unions of closed sets. Yeah, so it is some subtlety about the topology in this business. So to know the localizing tensor ideals, you only need to know the spectrum as a set. But if you want to know the thick tensor ideals, you need to know the topology in this space. Yeah, it's just a remark. Okay, so yeah, so what's known? Examples that yes, okay. This is from and then, yeah, I just erase it. Yeah. You can also describe what's a big support data, satisfying certain conditions, and you have maps which compare the big support data with this Balmer-Favi support. And in many cases, it's if you can check some bijection between the spaces, automatically it will be an homomorphism, and then I mean, you have a way of comparing previous examples which were not done using this Balmer's support. You can compare them by using some techniques with the previous examples. Because the business now is, well, on the one hand, is to classify localizing tensor ideals. On the other hand, is just identify the Balmer spectrum. You know the object, but it's an object which is defined abstractly. And you would like to know in each of your contexts if you could identify it with some natural choice in the example you are working on. Yeah. So for example, sorry? You switch for, yes. This is 3. Yeah, so. No, okay. Yeah, so so let's, since we started with the the work of Hopkins Smith on the finite spectra. So one of the lines that you can go is just, instead of looking at just spectra, you take a finite group G and look at equivariant setting. You look at G equivariant spectra. And then what can you say from these categories in a G equivariant setting from the non-equivariant one? Yeah. So let me. Okay, so I will finish. Yeah, as I said, there is a way in their work they develop a way. Oh, okay. Oh, I did well till the last 5 minutes. So it's yeah. Okay. Yeah. So develop conditions to compare support data like X sigma as before, but in this context, not essentially small, just support data to Balmer's support data. And in this way, you can identify this in the previous examples. For example, in the Benson, Iyengar, Krause, then you can show that the Balmer spectrum is the spectrum of homogeneous prime ideals in the cohomology of G, and in the other context. So there is kind of this stratification business kind of gets into the directions. First, go to the localizing ideals, and on the other hand, try to say as much as possible about the Balmer spectrum and its topology. That's the way. So let me. Let's go to an equivariant setting. Yeah. Yeah. So let me finish just with a few remarks about what can be done in the equivariant setting. And you can look at, you have G finite group, and you can look at spectra with an action of G. I'm not going to go into the technical definition, but I think the idea you have in your mind now is correct for what I'm going to say. And I'm looking at this category, and then there are a goal of several people that has approached the study of the Balmer spectrum and the stratification for this category. So I'm going to write several names. There's Barthel, Greenlees, Hausmann, and also that's okay. This is Barthel, Hausmann, Naumann, and Nicolaus. This is a Nicolaus and Stapleton. And then Balmer and Sanders. This is the reverse chronological order. So that's that they describe the primes for this in this tensor-triangulated category. And just to give you an idea, it's just the primes in the spectrum are described. First you just take P local, just fix a prime in the same way we were doing in the case of the non-equivariant setting. And then, in this case, the primes are indexed by a subgroup and an N. And the business goes by looking at geometric fixed points of the objects. Yeah. So the primes are defined by N fin such that. And then here you look at Morava-K theory again, like in this Hopkins-Smith type for a spectra. But now here you look at geometric fixed points on X. This is 0 for M less than N. Yeah? So this is how the primes looks like in the spectrum in the covariant setting. Yeah? And you can see here that how the geometric fixed points appear. So this kind of descent now goes to taking geometric fixed points. Yeah? And just let me give you, this is front, and this is something we have been working with several people. So it's Barthel, myself, Hart, Nico Naumann, and Luca Paul. Yeah. Just to describe some descent techniques for different settings in this equivariant world to obtain stratification in the equivariant setting from the information that you obtain from the geometric fixed points and a descent technique. Yeah? So I will just write it so you see how it looks like, because it reminds of this, of the previous descent. Then you have a finite group, and R is now it's going to be a commutative ring, but in G spectra. Yeah, so commutative ring in G spectra, and here you take a family of subgroups. That means that it's closed under conjugation and overgroups. Yeah? And take a family of subgroups with, no, not overgroups, just, no, sorry, yeah. Yeah, exactly, subgroups, sorry, I got it wrong. A family of subgroups such that R is F nilpotent. That means that the module category for R can be built out of the orbits G mod H for those H which are in this family. Yeah? Then let's assume two conditions. First is that the Balmer spectrum for category of modules where you take fixed points for every H in this ring is noetherian. For each H in the family, and you assume that those module categories, when you take fixed points, are stratified. Then mod R is stratified. With an Athenian spectrum, which is compact here. Yeah? So in the covariant setting, the idea of the descent techniques goes by taking this family of subgroups for which your ring is F nilpotent. You see this F nilpotent, F isomorphism. I mean, it's like it mimics a bit. That comes from a paper of Matthew, Noel, and Naumann. Yeah, and it's this nilpotent and descent, I think it's called. And then once you have one of such family, and they describe for each spectrum, they describe in most cases which are the smallest family of such of nilpotent, then you can, by studying the fixed points, the geometric fixed points on the spectrum, the information that you get there can be promoted to the big category. Yeah? And also just obtain a description. That the other point is, as I said, try to say as much as you can about the topology of the Balmer spectrum. And then what you obtain is that mimicking Quillen's classical result, you can obtain results of this type describing on a strata where you have the Balmer spectrum for the compact objects in the module over the fixed points of the ring. So you rely on the fixed point, the geometric fixed point, quotient also by the action of some automorphisms coming from conjugations in G. And this is a disjoint union. So in this setting, you also can make an analogy which Quillen's strong stratification theorem. Yeah? And so we described, just to finish, we described some examples. We were describing, but I don't feel much comfortable yet with this because it's very new for me that I'm learning about this Lewin-taped En. That's one of the examples we have been working. And a nice example is just equivariant K-theory. And given any spectrum, you can make the Borel version of it. So the Borel versions, you have kind of honest G-equivariant thing, and you have the Borel versions of ordinary cohomology theories, and then these are the type of examples we are working on. And then this is useful? Well, first it gives you the idea is that you get kind of a way of reorganizing your category using some principle, which is you have this topological space, which is the spectrum of prime ideals, and you have this kind of stacks, right, given by these primes. And this gives you kind of reorganizing your information. And once you have this classification, you can approach some conjectures, like the telescope conjecture about localizing a smashing localizations, and then you can show that if you have such a smashing, you have a notion of a smashing localizing subcategory, then you can show if you have a stratification that it's generated by, it's compactly generated, that it's generated for compact objects, for example, that it's the classical corollary that you obtain out of this business, right? Okay, so I think I will stop here. So thank you very much.